Here's a pendulum problem that we are trying to solve today. It's a classical vibration issue. Uh, this is a pendulum which is having the mean line, and it's having a swing with a mass of blob attached. The angle that this makes with the mean line is very small. Let's call it as theta. And what we need to do is, in this problem, we need to find the length of this pendulum. So what should be the length of this pendulum? If the time period is 1 second, so tau is the time period. This is given as 1 second, and we need to find the length of this pendulum. So first we need to derive the equations, and we can use many different ways, many different methods to solve this problem. We in this solution we are going to use the energy method. So according to the law of conservation of energy, you can say that total energy in the universe is going to remain the same, so there's no change in the energy of the system. So in a way, the potential and the potential energy plus the kinetic energy, total energy change is going to remain the same. So d by dt of t plus v is equals to 0. This is the equation we are going to use. But first we need to find the kinetic energy and the potential energy that is there in our system, which is a simple pendulum. So let's first find the kinetic energy. So T is equals to half mv square. So this is half m. So x is the distance that this blob will travel. So let's say this is the distance x. Okay, and x dot is the velocity. So mx dot square is the kinetic energy, half mv square. So in terms of L and theta, how much is x? So let's look at this. Suppose this is another the mean line, okay, and so this blob will travel in circular arc type of fashion. Okay, suppose this will end up over here when it reaches the mean line, and what we need to do is we need to find this distance. So this distance is, according to the trigonometry, you can say that this is about L sine theta. Okay, so L sine theta is equals to x, but for theta which is very less, then sine theta can be written as equals to just theta. Okay, so then x will be equals to L theta. The kinetic energy is then written as T equals to half m L theta dot square. Okay, this is the kinetic energy. The potential energy V is basically because of the height of this pendulum. So it's going to be mgh, or in our case mg times basically the distance. This distance over here, this distance that it has been elevated. So this distance is h in our case. So if you look at the triangle, you will see that this is the triangle, this is the h, okay, and this distance is what we want to find. Okay, so h is what we want to find. Basically, if you look at this, um, you will see that v equals to mgh. So in other words, we can write v equals to mgl minus mgl cosine of theta. Okay, so you can see that this is the L distance, right? And if you consider this whole triangle, then this will be equals to the L cosine theta. So L minus L cosine theta. Okay, so this distance, the rod of the pendulum is going to be L, and this portion over here, this is L cosine theta. This is L cosine theta. Okay, so what you have is mgl cosine theta. Okay, or mgl is common, 1 minus cosine of theta. Okay, so this is your v, and we already have found the expression for the t. So d by dt, there's no change in the total energy in the system, is equals to t, that is half m l theta dot square plus m gl times 1 minus cosine theta. Okay, this whole thing should be equals to 0. So let's take the derivative with respect to time. First, what you have is half m l square theta dot square derivative with respect to time is nothing but 2 theta dot, okay, times the derivative of theta dot itself, which is going to be theta double dot, okay, plus m g l. Okay, so just mgl with respect to time t is 0. So if you multiply inside the bracket, what you'll have is mgl cosine theta, and cosine theta derivative with respect to time t, what you'll have is sine theta times theta dot. This is whole thing equals to 0. Okay, so again you can replace theta with theta if it is very less, then sine theta will be equals to just theta. Okay, so in this case, since theta dot is not equals to 0, the rest of the terms will be 0. So what you will end up with is, after simplification, L theta double dot plus G theta equals to 0. This is like the characteristic equation of differential equation of a simple vibratory system. Okay, and from this you can simply say that putting it in the normalized form, you'll get theta double dot plus G by L times theta equals to 0. This is very similar to the normal equation, which is x double dot plus omega n square x equals to 0. This is the characteristic equation. Now from this, comparing these two equations, you can say that omega n square equals to g by L, or omega n equals to square root of g over L. Okay, so this is the derivation for natural frequency of our system. In series of problems after this, we'll try to derive the same equation using other methods, like Newton's second law. Okay, again we should end up with same equation or same expression for the natural frequency of our system. So now to solve the problem, what you can say that omega n will be equals to twice pi over tau. So this is expression you can get easily from omega n equals to twice pi f, okay, where f is equals to 1 over the time period tau. Okay, and you know that the time period in our case is equals to 1 second as given in the problem. So omega n is equals to 2 pi, which is 6.283 radians per second. Okay. Now comparing this, so you get the omega n, you can directly put that in the expression and you will get the length of the pendulum. So length of the pendulum will be equals to g over omega n square, so which is equals to about 24.85 centimeters. So in order to have a time period of 1 second, the length of the rod of the pendulum or the clock should be about 24.85 centimeters. Thank you.